We are for lesson 10.1, Sequences, Series, and Sigma Notation, Student Notes. The learning targets are that you are able to investigate different types of sequences to identify patterns and find additional terms, and that you can use sigma notation to represent and calculate sums of series. A sequence is an ordered list of numbers. An ordered list of numbers, usually with a pattern. Doesn't always have to have a pattern, but usually they'll have a pattern with them as well. A finite series, or a term, is a number in a series or sequence, and we'll be getting to sequences in the next section. So we're going to get a little bit of vocab out of the way as we start to use these terms. These should be somewhat familiar to you, though, from Algebra 1 and Algebra 2. A finite sequence has a set number of items. Actually, a set number of terms. For example, 11, 22, 33, 44, 55 is a sequence of numbers that has exactly 5 terms. A first term, a second term, third, fourth, and fifth term. It has a finite number of terms versus an infinite series that has terms that continue infinitely. Such as 1, 2, 3, 4, 5, and so on. The ... representing that this sequence continues on beyond the number 5, beyond the fifth term. We're going to talk about explicit and recursive. Explicit formula is a formula where you're finding a value based on the position of the term. So finding, normally we call it an output, but finding a sub n, which is, it's actually written, hold on, we're going to write the formula for that. Finding an output for position n, maybe it's the first position or the third or the fifth or some random position, where n is the position, or for position n, based on that position. So we would say a sub n, that's a subscript, equals some function of n. We'd have some function of n. A sub n would help us calculate the output for the nth term. I wouldn't need to know any other terms other than the explicit formula. I could just use the formula if I knew which term position I wanted. For example, for this one, the explicit formula would be a sub n equals n. So if I asked you to tell me what the 100th term is, well, the first term is 1, the third term is 3, the fifth term is 5. The 100th term would be 100. Now, I don't need this pattern to see it if I was already told this rule. Whatever position I want, I just put it right there. That's my output for that position. For this one, it would be a little bit different. This one, the explicit rule would be a sub n equals 11n. So without even knowing the rest of these numbers and seeing the pattern as I go left to right, I would just say, hey, this right here, this fifth term, you want the fifth term? Just plug it in here. 11 times 5 is 55. You want the third term? Plug a 3 in here. 11 times 3 is 33. So that's how the explicit formula works. The recursive formula, which we'll get to in a second, has to do more with what's called the recursive pattern, which is how do I get to the next number from the previous? Here it's add 11, add 11, add 11. Here it's add 1 each time. So using the recursive pattern, and so you're wondering, well, what does recursive pattern mean? What I mean by that is how to get the next term from the previous term. Well, here we have 32 and then 16, and then 16 and then 8, and then 8 and to 4. So there is a pattern there. Some of you see it right away. All they're doing each time is dividing by 2. So that gives us an explicit rule, which, well, that's the recursive pattern, sorry. So our next 4 terms would be 2, comma, 1, 1/2, 1/4. There are our next 4 terms if we continue the pattern of taking the previous term and dividing by 2, dividing by 2, dividing by 2. Try the next one. Take a moment to pause the video and try the next problem to see if you can figure out the pattern. Welcome back. All right, so most of you might have tried initially to times 2. 1 times 2 is 2, 2 times 4 is, or 2 times 2 is 4. 4 times 2 is not 7, so that rule did not work, that recursive rule. However, we could add 1 and then add 2, and 4 plus 3 is 7, and 7 plus 4 is 11, plus 5 is 16, plus 6 is 22. 22 plus 7 gives us the next term, 29. 29 plus 8 gives us the next term, 37. 37 plus 9 gives us the next term, 46. And 46 plus 10 gives us the next term, 56. So there are my next 4 numbers, and I did this by adding increasing integers to them. That is the pattern to get from one to the next. Finding the next the first 4 terms in the sequence. So this time we're going to use the explicit formula because they give us a rule that has a sub n and just n in it with some other operations. So what I'm going to do is I'm going to have to find a sub 1, a sub 2, a sub 3, and a sub 4. A sub 1 is going to be found by plugging in position 1 into the formula. 1 cubed is 1, minus 10 is negative 9. 2 cubed is 8, minus 10 is negative 2. 3 cubed is 27, minus 10 is 17. And 4 cubed is 64, minus 10 is 54. So our next numbers, the first 4 terms are negative 9, negative 2, 17, 54. Those are the first 4 terms of this sequence. Recursive formula. Recursive formula is where the terms are based on previous terms, not the term position. Not based on term position. Based on previous terms. That's plural. It may be based solely on the previous term, or it might be based on several previous terms. We don't know yet. It just depends on the sequence. So when I'm looking at this, we're going to have a sub n, which will be a function involving n minus 1. It'll involve the expression a sub n minus 1. If you see that sub minus 1 or the subscript n minus 2 or subscript n minus 3, that means go back to 1 previous position, or if it was a 2, 2 terms back. Or if it was an n minus 3, it would mean 3 terms back. So if I were going to find a sub 5, and it involved something with a sub n minus 1 and a sub n minus 3, then that would actually mean don't plug 5 in here for this, but actually go back to this means 1 back, so that would mean go back to the 4th term. So what is the 4th term? Plug it in there. And this would mean go back to the 5 minus 3 would actually be the 2nd term. So I'm not going to plug the 5 in and add those. I'm going to figure out what the output is in position 4 and in position 2. So find the 6th term in each sequence. Now, I'm going to look at this one, see the subscript of n minus 1, that's how I know it's recursive. Versus the other problem that we had above, which had just an n in it. There was no subscript in the actual formula. A sub n is the same thing. You're finding an output. A sub n, you're finding an output. But in this case, it's just based on the position and some operations. That's explicit. In this case, there's a subscript instead of just an n with the operations. So our first term is 3. They want us to find the first 6 terms. Well, the first one is 3. So this means take this formula right here. That means do -2 times, remember a sub n minus 1 means the previous term. If it was a sub n minus 2, it would be 2 terms back. A sub n minus 3, 3 terms back. So I'm going to take the previous term, 3, and I'm going to multiply it by -2. I get -6. I'm going to take that previous term, -6, and multiply it by -2 to get positive 12. I need to do 3 more of these to get the first 1, 2, 3, 4, 5, 6 terms. So 12 times -2, -24, positive 48, -96 would be the 6th term. Now, they actually didn't ask for the first 6 terms. They actually asked for the 6th term, so our answer would be this. But unlike an explicit formula where I would have just said, oh, plug 6 in, I can't do that. There is no n in here for me to say, oh, plug an n in. It's -2 times a sub n minus 1. Well, that means that I have to do -2 times 6 minus 1 would be the 5th term. -2 times the 5th term, which was 48. But in order to find that 48, I had to find the 3rd term, or the 4th term. And then to find that, I had to find the 3rd and the 2nd and so on. So with recursive, you have to follow the pattern, or the pattern, the recursive rule, to get the next term until you get to the position you want. Letter B. Letter B, you look at it and you say, well, is it recursive or is it explicit? Explicit would just have n. You see this a sub n minus 1, which means the previous term. So if I want the 6th term, I have to know what the 5th term is so I can multiply it by 2 and subtract 7. So I'm going to have to, by the way, this n greater than equal to 2 tells me that this works only for terms 2 and up. Term 1 has to be given to use the recursive formula. So here we go. This first term is 8. What this rule does is it says 2 times the previous term minus 7. They're basically describing for us the pattern on how to get from one number to the next when they give us a recursive rule. So 2 times 8, 16, minus 7. 2 times 16 minus 7 is 9. So now, 2 times 16 is not, it was 8. 2 times 8. 2 times 8 minus 7 is 9. Okay, 2 times 9 minus 7, I said the wrong number, confused myself, is 11. 2 times 11 minus 7 is 15. Then I can times it by 2, and minus 7, I get 23. By the way, on your calculator, if you have a lot of numbers that you have to do this with, you can just keep going in your calculator. Take that previous number, times 2 minus 7 is 39. So we have position 1, 2, 3, 4, 5, 6. This is the 6th term. That's what they asked me to find was the 6th term. So the answer is 39. A sub 6, the output of the 6th position is 39. Here, A sub 6, the output of the 6th position was negative 96. Next, we're going to talk about functions that converge versus diverge. A function that converges So converges, you can think of what that means physically, to converge versus diverge, to come together versus to divide apart. To come together, to converge, means that the sequence has a limit. It's as the terms approach a specific number. Or it approaches a specific number. To you, what we've had limits with, when we first started, even in pre-calc, we started with limits, is we looked at rational functions. And as you increased towards this x value, which had a vertical asymptote, as you got to that would actually be divergent, sorry. As I went in a negative direction on x, as I got more and more negative values for x, we saw that it approached a specific y value, a specific output. We're not looking at graphs of rational functions, but we are looking at things that could have explicit rules. But we're going to be looking at these patterns and deciding, do they have a limit? Are those numbers getting closer to something? Are they going to converge on a number or, approach a specific number? Or are they going to diverge, which means that they'll just keep growing infinitely, either in a positive or negative direction? It would be having no limit, usually meaning, in terms of our functions that we've seen so far, that they'll keep growing infinitely, or keep increasing infinitely, or keep decreasing infinitely when we're talking about the range, the outputs. So here's an example of converging versus diverging. Determine whether the sequence is convergent or divergent. To do this, you may actually have to explore it a little bit. So for this example, I have 64 over 2n, and some of you are already like, well, I kind of know what that looks like. Some of you are going, what? What is he talking about? So when we talk about this being convergent or divergent, some of you might recognize that as a rational function with a vertical asymptote and already know, hey, there might be something here. And you might recognize that it has a horizontal asymptote also, or not. Not for that. So anyhow, a sub n equals 64 over 2n. Well, I can plug in some values. This is an explicit rule. I know it's explicit because there's just an n, no a sub n minus 1. This one over here is recursive. But that's not what we're asked. We're asked to determine whether they're going to converge, have a limit, or be divergent. Well, I'm going to do the first position and the second position and so on. So I'm going to, in my calculator, since it is an explicit rule, I could actually use my calculator to help me get these quickly. Do 64 over, in parentheses, I have to put 2x so that it divides the whole thing, not just the 2. And I'm going to go to my table, and I'm going to plug in 1, 2, 3, 4, and I can just keep plugging in numbers to look for a pattern. And I see, yeah, it's getting smaller and smaller, and then the question is, well, is it just going to keep decreasing infinitely? You might not be sure, so you just keep exploring a little bit more. You might even jump in numbers. Maybe now I'll go by 2's instead. 14, 16, 18, 20, 22, 24. So I had 24, now I'll do 26. They're getting smaller, but not by as much. 27, 28, maybe 30, maybe 40, maybe 50. They keep getting smaller and smaller. Maybe 100, maybe 200, 300, 5,000. Okay, that number right there, 6.4 e to the negative fourth, is basically, it's not exactly, there is something there, but it's very close to 0. 10,000, or more actually, still a positive number, virtually 0. So what's happening is, yes, they're decreasing, but the increments they're decreasing by get smaller and smaller. And they never go negative. So it's not going to decrease infinitely, it's going to approach 0. So this one is convergent. It approaches 0. The limit of a sub n, or sorry, as n increases in value, the limit of a sub n is 0, meaning that's the number it approaches. Let's take a look at our next pattern. I'm not going to use my table to get this one because this is recursive. So I'm actually going to use my calculator by plugging in the first value of 9. And then it says take the previous term and add 4. So I had 9, 13, 17, 21. These just keep going up by 4. They're equally spaced apart. It's not increasing much. It's increasing by a constant amount. It's not increasing by smaller increments each time. So when I look at this, I know that this one is going to increase infinitely. It's just going to keep going up and up and up, so I know that this one is divergent, which means that there is no limit. Take a moment to pause the video and try the next two. Take your best guess as to what you think it does, but explore it in the table first. All right, as I look at this next one, I have 3 times -1 to the power of n, which I'll put in my calculator as 3 to the negative first to the power of x. So now I'm going to put that into a table format, and I'm just going to plug in 1 and 2 and 3 and 4 and 5, 6 and 7 and 8 and 9. And this one's fluctuating between 3 and -3. It keeps going back and forth. Well, that makes sense because when I have an odd power, I've got, when I have an odd power, the number's going to be negative. When I have an even power, it's going to be positive. So it makes sense it's fluctuating between 2 different outputs. So you're going, okay, it's not increasing infinitely, it's not decreasing infinitely, but let's go back to what it means to be convergent. To approach a specific number. It's actually not approaching anything. It's equaling one of 2 numbers. It's not incrementally approaching a number like it was here, where it continually got closer and closer to 0, as we saw on our graphing calculator. So this one, even though it's the same 2 bouncing back and forth between 2 different numbers, is divergent. To be convergent, it would be incrementally getting closer and closer to a specific number, not 2 different numbers, as we see here, bouncing back and forth. For letter D, that one is an explicit formula. So again, you could use your calculator. You would do 0.1 to the x power times x divided by, and I got to put this in parentheses, 2x minus 1. Now, some of you said, well, there's an n minus 1, but that's not a sub n minus 1. A sub n minus 1 is the previous term. So this is an explicit formula also. So both C and D were explicit. But again, the question is whether they're convergent or divergent. So we're looking at this thing going, okay, well, it's, that's going to happen. And as this gets bigger, that decimal's going to get bigger, which is going to make this number on top smaller. Then you're dividing by something. I don't know. Let's see what happens. So I'll pick some numbers to put in. And I might put in 1. I get 0.1, 2, 3, 4, 5, 6, 7. Okay, I'm noticing that these are all, virtually 0. They're not 0. They're very, very, very close to 0, though. So now I'll put in some bigger numbers just to see 100. Okay, 100 gave me 0 on my calculator. I think only because, well, there's reasons why. You'll get there later. But as I see this, that's getting closer. Let me see if I put 200, 300. So you can see they were incrementally getting smaller, smaller until they reach 0. So since this approaches 0 as we go down, this one is convergent. And if we were writing limit notation, which you'll be doing a lot in calculus, limit as n approaches in positive infinity on a sub n is 0. That the numbers get closer and closer to 0. As of for right now, though, they just wanted you to state whether they're convergent or divergent. Tomorrow we're going to be looking, or in the next lesson, we're going to be looking at writing explicit and recursive formulas. So your assignment that goes with day 1 of lesson 10.1 will include page 595, problems 1 through 27. And that is something that will be done along with this lesson. Have a great day.